Does our choice of closure, class-based object, or generator coroutine affect usability? Absolutely. It affects usability because it is almost always the case that when we have a choice in Python between two ways to accomplish the same goal, for example, writing a function with def or writing a function with lambda, or building a list with a for loop or building a list with a comprehension. If one of these two ways is more restrictive than the other, the lambda can only have one expression, whereas a def-based function can have as many expressions as it wants. The lambda can only use the expression grammar, whereas a def-based function can use the statement grammar as well. A list comprehension can only have one expression in its, or can only use the expression grammar in its target. It can't use the statement grammar, and it can't refer to itself as it's being built, whereas a for loop can. In all of these cases, when we have two ways to do the same thing, but one of those two ways is more restrictive than the other, we will generally find that the more restrictive approach can lead to greater usability and greater readability, because when somebody comes across the more restricted formulation in some code, there's fewer questions for them to ask themselves, like, what else could this thing be doing? Is this thing deeply stateful? Well, if we're talking about a for loop versus a list comprehension, if it's a list comprehension, no. There's significant limitations on how stateful this thing can be, because the structure, the formulation that you're using, cannot refer to itself as it's being built. Does this thing have a try except in it? Well, if you're given a lambda instead of a def-defined function, no, because you can't use a try except in a lambda. That's part of the statement grammar. If the thing that you're given is a closure or a function with a closed over state, do you have to ask, does this thing implement more of the object model? Are there other protocols that I need to be aware of? No. It'll be very difficult for somebody to implement that. They probably haven't. If you give them a generator coroutine, you don't have to ask, well, what are all the different modalities and the different parameters that can be passed in? Generator coroutine, you can only send one thing in. Whereas if you give them the class-based object, well, a lot of other stuff could be happening, and they naturally might be curious and they might need to dig in order to feel like they have a solid understanding of what this entity is. By giving them that class, you are giving them something which is capable of doing everything which the other formulations are capable of doing, but requires that they carry a little bit additional burden of, how does this thing actually work? What else is going on here? Do I need to read the documentation for this? Whereas with a function or a generator coroutine, you call the thing, you do a .send, or a next on it. There's really not much more you can do. What is the difference between inheritance and composition? And which do I pick? Well, let's take a look. If we have a base class, we can inherit from that base class in some kind of derived class. And this means that the derived class automatically gets methods when those methods are added to the base class. If the derived class wants to customize some behavior on the base class, well, it can do that, and it can use mechanisms like super in order to refer back to the base class's implementation. And so here you can see derived automatically gets the method f from base, and if I later add the method g, either in a later code commit, or if I add it dynamically at runtime, well, this derived class automatically gets that g method. If I want to customize this, well, I just write my f method here, and then I can refer to the original base class's f method using the super mechanism. Fairly straightforward. Do note that when we inherit, we not only inherit methods and this functionality, we also inherit the meta class. And so if this base type had a meta class here, note that the derived type is going to inherit that meta class. The type of the base type itself and the type of the derived type itself is the same meta class. This is why we often see the meta class used, or historically at least, we often saw the meta class used as a mechanism by which to enforce constraints down a type hierarchy from a base type to a derived type. These days, we have a better way to do it using a init subclass, and so the meta class no longer is the safest way to accomplish this. It's instead one possible way to accomplish this, and the only way for us to implement the Python vocabulary on a type itself as opposed to on an instance. Setting that aside, note the other way that we typically consider to combine some functionality between two units, two classes, is the composition example. We have some component. In our composed, we take that component and then we dispatch the pieces of that component in explicitly written instance methods. Note that if some functionality is added here later on, we have to explicitly make it available. Everything has to be made explicitly available through our composed interface. We don't automatically get any functionality. Now, of course, since we're making this explicitly available via some function like this, well, we can customize it as we see fit. There's really no limitation that we customize this, and we don't have to use any mechanisms like super. Note that the inheritance mechanism or the inheritance formulation has one other feature, which is we get a default implementation of isInstance. In the case of a base type and a derived type, well, this object is an instance of the derived type, and it also is an instance of the base type, and the derived type is a subclass of the base type. The isInstance protocol and the isSubclass protocol have been implemented for us in a way that makes a lot of sense to us if we've used any sort of inheritance mechanism in any other programming language. But do note that we can customize isInstance and isSubclass. These are protocols like any other. So we can create our own metaclass with an instance check and create our own class with that metaclass. And given this implementation, we can see that anything now is an instance of this T without having to actually be strictly derived from it. The number 1, 2, 3 is an instance of the T because it's just calling my instance check here, which always returns true. I could return false here, or I could actually look into the entity that I am given and try and determine based off of methods that I see. Because we can customize instance check, this means that if we need some object to be able to say, I'm an instance of some interface, we do not need to use inheritance to accomplish that. And we also don't need to use clumsy call site has adder calls. We can instead implement this using inheritance or composition and then create some interface representation, basically a meta class with an instance check on it that says, oh yeah, this thing over here is an instance of me, even if it's not strictly inherited from me. Note that the instance check has some directionality. So while we can make anything look like an instance of T, we can't go the other way. We can't make an instance of T look like anything. We can't make this object look like an integer because the instance check doesn't work in both directions. It says, okay, I'll tell you if some object is an instance of me, but I can't make some object look like an instance of something else. And so here, there really is no way for us to make our custom object look like an instance of an integer without actually directly subclassing from integer. This is one reason why we may be required to use inheritance. We have some class, and we need to pass isInstance checks for that particular class, and that class is closed in some fashion where we cannot basically open up that class and change what its instance check does in order to make other things look like that. The only implementation that is available to us is the default implementation that looks at the inheritance hierarchy, looks at the method resolution order. In some very limited cases, we could maybe use class patching to make this work. For example, we could give this a brand new meta class and we could patch the class of the class. Although you can see here, it didn't work in this example, and there's going to be very, very few examples where we can actually see this work. Although class patching itself is not altogether a very uncommon thing for us to see in Python. In fact, prior to the introduction of module level getAttr and module level dir, this is one of the means by which we would make modules respond to getAttr or dir, those object model methods or those data model methods, to make them equivalent to any other type of object that we might have. Do note that we have options other than inheritance or composition. Because classes in Python are created at runtime, because the class statement in Python is executable code, well, we can do whatever we want inside that class body. We can dynamically create entries in the local state of this class body to create methods. So here you can see some code sharing between A and B that doesn't use composition and it doesn't use inheritance. It instead, we created two functions sitting out in the module scope, and we just brought them in here. And we could even do something that is as weird as this. Surprisingly enough, and this always surprises me, this syntax works. This is probably one of the only places I can think of in Python where we see a variable can have a different scope on the left-hand side and the right-hand side of an equal sign. In all the other places, it has to have the same scope. It always has to be a local, a global, or a deref. But in this case, you can see we're setting a local variable using a global variable on the right-hand side. What this means is, if we need to do some kind of code sharing, well, in the inheritance case, what we do is we'd create a mixin or a base class, and we'd bring it into these classes. And that has some other consequences, our instance consequence, our meta class consequence. And we may not even be able to see a very nice or clean hierarchy there. Well, if we needed to share some functionality, instead of putting that into a mixin, I just put it into a dictionary of these methods and just do a .update on the local state of the class body to introduce those into this class. This is what we might call the object construction approach, because we're really just viewing the construction of this class as something where we can set fields as we see fit, just like any other mechanical process. And in this case, we don't really need the traditional composition or inheritance approaches. Note that the object construction approach looks very similar to what we might think as the canonical use case of a class decorator. That is, to use a class decorator to add extra methods into something. And so here you can see very straightforward use of a class decorator to add a method f and a method g into this class here via some constructive approach. Otherwise, we could have this subclass from something that introduces the f or g. Well, the class decorator and the construction approach might be a preferable way to do this. We may, in fact, prefer to use that class decorator if we want to have a very light touch. Here's one interesting detail of the inheritance approach. When we use the inheritance approach, we automatically receive changes made to the base type. And that may be desirable. The reason that may be desirable is, if we think about our relationship to the entity that we're working with, the base entity in the case of inheritance, the base class, it's often the case that the base class is way, way, way more important than the derived class. That is to say, the base class might be something that is under very active development. It may be very, very large. It may have a lot of functionality, and it may add and remove functionality on a regular basis. The derived class might be less important from the perspective that it's relatively small, maybe just a couple of lines of code, and it's just taking that base type and adding one or two small details to it. If that's the case, well, do you really want to be reading the pandas change logs or the networkx change logs to figure out every single change that occurs in pandas or networkx in order to support your in order to support a compositional approach, composing a pandas data frame or networkx digraph? I don't think so. What you probably would want to do in a case like that is you'd want to say, look, I want to have a very light touch. I want to have something that's my directed graph type that just takes a networkx directed graph and does one or two small things to it. That's it. And as the directed graph in networkx changes, I want to transparently accept those changes. I'm pretty certain that that's going to work out for me because I'm doing something very small, very innocuous, very constrained. And so I don't mind if networkx's digraph adds another method. I'm fine to automatically take that in. In fact, I desire that I want to take this in because otherwise my custom class might in fact start to break when it's passed to other methods in networkx that then assume that certain pieces of functionality are available. Because if I instead did it like this, passing in this graph object, well, do I really want to implement nodes and then edges and then the next method and the next method and the next method? And there's like 80 different methods here. It's too much work. And it's too much work considering that if they gain another method here, I have to write one more thing explicitly here. That's not the relationship I have with the library that I'm trying to integrate, that I'm trying to wrap. If it goes the other way around, if the thing that you're trying to make use of is much less important, maybe much smaller, and the thing that you're writing is much larger and much more important, then you may see that the consideration is flipped. In that case, you might say, well, I have some class here, and it's just got one method, and it's just got one tiny piece of state, and I want to interact with it. And maybe this will change, but that's not a very important thing. I really want only one small piece of this thing here. So if it grows a G method, I probably don't want it. And if I do want it, I'll know that I want it. Well, in this case, this is where we might use a compositional example, because here it's very clear that we're more important than the thing that we're composing with. And if the thing that we're composing with changes, we want to explicitly pull in those changes. We know ahead of time which pieces we care about and which pieces we don't care about. And it seems to be the case that our composed class, the thing that we're writing, is of far greater overall importance to us. If it's the case that neither inheritance nor composition are quite working for us, for example, understand that when we use inheritance, well, we're setting up a hierarchy. And when we set up that hierarchy may not be correct to any generality. The canonical example that I use is if we were to take 3 entities and we're to try to classify them, say a cow, a pig, and a chicken. How do we group these into 2 separate groups? This would be a close relationship to how we would create some class hierarchy. And you could say, well, one thing we could do is create a mammal class, and class cow derives from mammal, and class pig derives from mammal. And then we'd create some avian class, and class chicken would derive from that. But we could also say there's a white meat class, and class chicken and class pig derive from the so-called white meat class here. And you could think that both of these are correct ways for us to organize these 3 entities. This is how we'd organize these if, for example, we're a veterinarian. We'll call it a vet, just so we can spell that. And this is how we'd organize these if it were the case that maybe we're a sommelier. Which of these is correct for these entities? Well, it depends on our use cases. In fact, the exact details of a class hierarchy and how the entities interrelate is so intimately related to how we would use these and what we're trying to extract, what details we're trying to model of these entities, that we might say that writing very, very deep class hierarchies is a bad idea if it's done outside of the most important part of our code. And in a very similar way that we might identify, do we want composition or inheritance based off which part of the code is more important, we might say, look, if what's most important is the modeling that's used for business purposes, then we should leave inheritance to the business use code. And at the library level, we should provide mechanisms like class decorators, or we should encourage people to use compositional mechanisms. If it's the case that people just do one small detail with the code that we have, and the most important thing is our library code, then in our library code, we might provide the inheritance hierarchy and then allow people to patch that in 1 or 2 small ways. Where the most important code is, where the most activity is, where the most development is, where the most lines of code are, these are all ways that we can identify which is the prime piece of this code, the thing that we're building on top of, or the thing that we're building on top of that. And based off of that, we may choose between any one of these approaches. Personally, I find that when these 2 approaches, inheritance and composition, are not really getting where I want to go, that's when I'll reach for object composition or one of those object construction or one of those constructive approaches. And thus, we can see we need a little bit of judgment, but it should be the case that we can identify quite readily which one of these do I pick.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.